Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover autonomous differential equations. So a first-order autonomous differential equation is in the form dy dt is equal to just a function of y. Now I have a couple examples of first-order autonomous differential equations right here. These things are first-order because they only contain first derivatives. They're autonomous because they only depend on y over here. As opposed to a non-autonomous differential equation, this is still first-order down here because it has a first derivative, but it's not autonomous because it depends on two things, both t and y. So, this, instead of just being some function of y, this is some function of both t and y. Now, we tend to use the letter t because these first-order autonomous differential equations are related to population growths, so we like to use the parameter t for time. But, I could say dy dx would be equal to 2x times y minus 4. So now this would be a function of x and y, still making it not autonomous because autonomous means that it's the right-hand side is only equal to its, to its dependent variable. So what I'm going to do is we're going to do some phase portraits and graph some of these using numerical methods. In this example, I want to determine equilibrium points, which we can also consider critical points algebraically, and then using the graph of y versus f of y to classify each equilibrium as stable, unstable, semi-stable by drawing phase lines and sketching several solutions. I know I didn't define these, but through this example, I will define what these things mean. So what I want to do is I want to graph this by graphing really like the tangentials of this function over the x, over the ty plane, t being the independent, y being the dependent plane. So that's really my goal, is to, I want to graph this thing. This would be the t-axis, this would be the y-axis, and I want to know what solutions look like. Are they going to be, curves, parabolas, exponentials, trig functions, who knows? So, first thing we know is that we have to find critical points, and if we remember finding critical points in, say, a calculus 1 class, we know that is when the derivative is equal to 0. So really, our equilibrium points or our critical points, this will happen when, the derivative is equal to 0. And remember, the derivative is equal to 3y. So when 3y is equal to 0 means, this means y is equal to 0. So this is going to have an equilibrium at y is equal to 0. So this. The slope will be equal to 0 when y is equal to 0. So this is the y-axis. Y equals 0 is right here. So the slope would be equal to 0 there. So what I'm going to do is I'm going to draw a bunch of tangential lines. I really guess I didn't need to draw it as a solid line. A lot of times we just do like tangentials here. But I really want to highlight that equilibrium point. Now it says to graph y versus f of y, and what I mean by that is I want to graph this as, this function is our y, then f of y. So this is going to be equal to, f of y is equal to 3y. That's what I mean by graphing this. That f of y versus y means that this is, I'm going to kind of treat this as the independent variable, and this is the dependent variable, and I want to graph this. Because if I'm going to get these tangentials, I need to know their slopes. Are they positive? Are they negative? I already know where they're 0. So if I can graph this, I can figure out, when these things are positive, when these things are negative. So this will look something like so. So this is going to be y, this is going to be f of y, and I know that 3y is very similar to graphing like in a basic algebra class, just the same thing as graphing 3x. So it's going to look like this. Our 3y is going to look, let's put it in different color. So our 3y is going to be this. Okay, so what does that mean? Okay, well, it means that anything, below y equals 0 is going to be negative. Anything above y equals 0 is going to be positive. And And really what this means is as you get further and further this way, you're going to get more negative. And remember that 3y is equal to the slope of this thing, right? So really these, the outputs of this function, that like f of y is equal to 3y. So the outputs of this function really represent what the slope is going to be equal to. So we already know right here when y is equal to 0, the slope is going to be equal to 0. And say when y is equal to -1, well, this is 3 times -1, so this would spit out -3. So that means the slope is going to be equal to -3. So when y is equal to -1, let's say down here, when y is equal to -1, I know its slope is going to be equal to -3. So I'm going to draw this way. I'm going to kind of do a slope here. That's what I'm trying to do is I'm trying to go down 3 over 1. I'm trying to find the slope of -3. It might not be steep enough, but we'll say close enough. Now, since it's an autonomous differential equation, it doesn't matter what t is. The slope is going to be the same for all t values. So whenever y is equal to -1, I'm going to have a bunch of slopes of -3. Now, if I go further, what if I say y is equal to -2? Well, on this graph, -2 is right here, right? So if y is equal to -2, then, this is going to plot 3 times -2 is going to be -6. So it's going to be, remember that this is representing, this output is representing what the slope is. So at -2, I'm going to have slopes of -6. So this is going to be really steep. So and we can see that as we get more negative, it's going to, as I get more negative, the slope is going to be more negative as well. And if I had like -0.5, say, let's say a third to make it real easy. So if y is equal to, say, -1/3, which would be about right here, I can see that this is going to give me, -1. So if I was at y equals -1/3, I'm going to have slopes that look like, just -1. Now we don't usually do rational inputs. I'm just trying to show you that as we go this way, we can see that the slope is actually leveling off, because what I know here here the slope is equal to 0. So I'll leave them in here, though. We don't usually do that at like a third. We usually do like -1, -2, -3, and so on. But since they're so steep, I want to really show what this thing does. Okay, now how about when they're positive? Well, if I pick +1, we know we're going to get an output of +3. If I pick +2, we're going to get an output of +6. So very similar to these things being negative. If you go in this direction, at 1, we're going to have slopes of +3. Boy, they should be steeper, but just pretend that's a rise of 3 and a run of 1. And then we also know at 2, very similar. If it's at 2, we're going to have 6. So this is going to be really steep. And again, the reason why I can draw it across here is because it's an autonomous differential equation. The slope doesn't depend on t. It only depends on what the y value is. Okay. So it says find the equilibrium point. We did that. So the equilibrium points were right here as y is equal to 0. And we can see that. And what they mean by that is if we had some floating point on here, if I'm asking for a solution to this differential equation, solutions to differential equations really kind of depend on where you live in the graph. What is your initial value? Well, if I have an initial value of 0, say I say, y is equal to 0. So if I go negative, let's say t is equal to, what's the point? Let's say -3, 0, for instance. So that would be, -3, 0 is going to be about right here. And what would happen if I popped a point in here? What would the solution to this differential equation look like? Well, it's going to follow these tangentials. But on this line, since it's equilibrium, it's just going to follow that horizontal line. That's what we mean by equilibrium. It's not going to move. It's going to stay at that particular point. What if I pick another value? Let's say -2, 1, for instance. So t would be equal to -2 right here. Y would be equal to 1. So what if I was at that point? Well, what would happen? Well, the solution to this differential equation, it's gonna, it's got to cross this and it's got to follow these tangentials. So we can see that it's going to do something like this, isn't it? And then if you go, more negative, it's going to approach that equilibrium point, but never really get close to it. So for this particular initial value, this is going to be its solution. And what happens if I pick the solution point? Now these are t comma y. These are particular solution points. So what if I pick, I don't know, 4 comma negative 2? So 4, negative 2, 1, 2, 3, 4, negative 2 is going to be down here, so it's going to look like that-ish. So again, that if this is kind of like water moving through this path, what's going to happen is as I move to the right, it's going to look like this, and as I move to the left, it's going to go toward that equilibrium, so it looks like so. So let's kind of talk about this equilibrium and really define it as stable, unstable, or semi-stable. So we read from left to right, and what I can see is that, if I put points here, they look like this thing is repelling, these curves. So this point is, going further away from the equilibrium. If I go off the equilibrium below it, it's going to go further and further away from the equilibrium. So we can see that it repels it. So in this case, we're talking about something that is unstable. It's unstable because it looks like this is, this is repelling. Repels. And then when they ask you to sketch several solutions, well, that's what I did here. This is one solution. Say if we went through this initial value, this initial value, this would be the equilibrium solution if I went through, the equilibrium for y, and then down here would be another solution. So these are 3 possible solutions. Now remember, there are an infinite family of curves here, so there's an infinite amount of solutions that go up, an infinite amount of ones that go down, just depend on your your starting point. So let's do another one. A second one, I want to do something more complicated that might have both stable, unstable, and semi-stable equilibrium points. So I chose one that had more than just one equilibrium point. It's got a bunch. So really remember, when I want to find our equilibrium points, we're really just determining, where its slope is going to be equal to 0. And remember, its slope being this thing. So I'm really just setting, so the equilibrium points is going to be, again, when dy dt is equal to 0, and this being dy dt, so this is when y squared times y squared minus 1 is equal to 0. And then we just use the techniques we learned in algebra to solve this this polynomial. So y squared times y plus 1 times y minus 1 is equal to 0. So I have equilibriums at, well, when y is equal to 0, that's when y squared is equal to 0. So if I say that, that's when y is equal to 0. And then, when y plus 1 is equal to 0, so y is equal to negative 1. And then finally, when y minus 1 is equal to 0, so when y is equal to positive 1. So these are my equilibrium points, which gives us some solutions or tangential solutions to this curve. So I know that it's going to be at 0. So let's do this, I guess, in blue. So equilibrium at 0. Which means if I did tangential points here, I'm going to have a bunch of horizontal tangent lines at that particular spot. Also negative 1, so at negative 1 right here, and also at positive 1. So right here, let's stretch this a little bit so it doesn't, I'm going to put some extra pieces in here. So again, this is another equilibrium, and this is another equilibrium. All right. Now, in order to figure out, the phases of this thing, I want to, is it, are the tangentials going up here or are they going down? Are they going up or are they going down? And in order to do that, I need to do this y versus f of y. So I really just have to graph this thing as a function of y. So graphing, f of y is equal to y squared times y squared minus 1. What we know is, we already know it's zeros. So it's at 0, this is at negative 1, this is at positive 1. I know it seems strange, students don't like this, but what I'm trying to do is, when this thing is positive, that means the slope is going to be positive. When this thing is negative, that means the slope is going to be negative. So I can use this graph to estimate the slopes over here. That's what we're trying to pull off. So graphing this f of y, there's really kind of a bunch of techniques to be able to do this. You can do your endpoints, but this is, or your end behavior is what I mean by that, and then your solution points. So we know that if I was going to look at the end behavior of this thing, this is going to be y times y times y, which is y to the fourth, it's positive. So the end behavior is going to go up. So it's going to be up here. This is just pre-calculus techniques. Now, when I go through this y equals -1, this is a linear root, which means it's going to pass through this thing linearly, or a straight line. And at 0, this is a quadratic 0, so that means I'm already below the curve, but it's going to go through that point quadratically. It's going to look like this. It's going to touch. And then similar, since this is linear, it's going to go linearly through that. So this would be the graph of this. So what that means is, remember, this is y, and this is f of y. So when y is negative, which would be down here, when y is below -1, I can see that I'm getting positive outputs. And actually, as I get more negative, these things are becoming more positive. So, and that represents the slope. So, right here, I'm going to have a slope of 0. I've already said that. At -1, this is going to be a slope of 0. At 0, it's going to be a slope of 0, and also at 1, it's going to be a slope of 0. That's why I have these equilibriums. Now, if I'm going more negative as far as -1 goes, I can see that they're really steep down here, and as I get closer and closer, they're going to kind of level off to this equilibrium. So over here, I know that the slopes are going to be smaller but positive. This is above this y. This is above this horizontal axis, so these are going to be positive. But as I get closer to the blue line, they're going to level off. And as I get farther away, they're going to be, steeper. They're going to be more positive. Their slopes are going to be steeper. And I'll do maybe one more. So as I get further away, we're going to be even steeper. So again, remember that the slope is equal to this thing. Now, in between here, I can see that we are negative. We're below that horizontal axis, but remember, it's close to 0 here. So when I'm close to this, they're going to be negative, but relatively flat. So they're going to be, when I'm close to it, they're going to be negative. And it gets the steepest at about a half. So if I was going to do a half, I can do the steepest here. So I guess that'd be, steeper here. And then when I get close to 0 again, they're going to level off. Now here again, they're still negative all the way through here. So I don't need this much. All I know is that these things are negative, so I'm just going to kind of draw them as negative. So I didn't need all three is what I'm trying to say. I just need to know its direction. I already know that it's gonna flatten out up here, flatten out down here. So I just need to know if it does this or if it rises. If it decreases or if it increases. And then similarly up here, I want to know if is it decreasing or is it increasing, because this is really an asymptote or an equilibrium. So I know that these things are going to be positive. So our slopes are going to be positive. And the further you get away, the further you get away from one, the more positive they become. Okay. So if I did a couple solution points, what would they look like? Well, I already know solutions at the equilibriums are going to be these blue horizontal lines. So what if I picked some initial values? Let's say this, t comma y. What if I picked, let's go up here. Let's say this is y is equal to 1, y equals 0, y equals -1. Let's pick 2. What about y is equal to 2? Now remember, it doesn't matter on t, but let's say -1 for it. So if I go to -1, so -1, 2, it's going to be this point. So what's going to happen is this solution point would look like this. It's going to follow these tangentials and go up. What if I was in between 0 and 1? So let's say, what if y was, let's say y equals 0, but we're at a half. Just making sure that my y values are between 0 and 1. So it would be like right here. Well, what would that solution curve look like? Well, it's equilibrium here, which these are asymptotes. So it's going to be asymptotic to that line, go down, asymptotic to this line. So that's what that will look like. Similarly, if I go, say, 2 comma negative 1/2, 2 comma negative half would be about, here. This would be 1, 2. Negative 1/2 is going to be about, here. So this is going to look like this. Again, asymptotic to these equilibrium points. And then finally, let's do one down here. So let's say 3 comma negative 3. So 2, 3, negative 3. This is 1, 2, 3. So about right here. So what's going to happen is, this is going to give us that solution curve. All right, so we've just, sketched several solutions. There they are. Now let's talk about, are they stable, unstable, semi-stable? So let's discuss this now. Okay, now when they're asking about that, they're asking about, each equilibrium as stable, unstable, or semi-stable. So looking at our horizontal tangent line solutions, let's look at the top one here. How about at 1? So at y is equal to 1, we can see, well, we have to ask ourselves, is it attracting, is it repelling, or is it doing one of each? So we can see that our solution curve here is, if I start over here, it is going away from that equilibrium. And same thing here, if I start here, it's going away from that equilibrium. So you can see that, this is repelling, which means, 1 is going to be unstable. How about at 0? How about this one right here? Well, this curve was getting closer to it, so it's attracting there. But unfortunately, this curve is going away from it, so it's repelling. So on top, it's attracting. On bottom, it's repelling, which makes it semi-stable. So y equals 0 is semi-stable. And then finally, at y is equal to negative 1 down here, we can see the curve is attracting, and this curve is attracting. So this is attracting. So since this is attracting, this is going to be stable. So if you like the content, please consider liking, subscribing, and sharing. Thank you.